Okay. Hello, everyone. Welcome to our book club session. So this week we are going to discuss a white paper, and this is basically Windows Azure storage paper. So I have shared a link with you guys where the white paper is mentioned, and also a video and presentation is made by the one of the Microsoft's individual. So I'm going to borrow his presentation. I think that presentation is available, so we can use that. So I'm going to take that presentation, and we will look at that and understand actually the design of Windows Azure storage. Feel free to interrupt me if you have any questions. Okay, yeah, so this is Windows Azure Storage, which is highly available cloud service with strong consistency. Did any one of you go through this paper or uh, these slides, or has anyone heard of it? Okay, so basically Windows Azure Storage, I think this paper is quite old. It's 2011's paper, but a lot of things are still the same, only some of the names have changed. Like now it's just called Azure Storage. So it is a service where you want to store any of your data in cloud, then you can use this service. So basically, what we're going to discuss today is like what are the data abstractions. That means what kind of data could be stored in this Azure storage. Then we will see a high level architecture of how actually it works, and then some of the design choices that were made while designing the system, right? So, uh, so basically, this Windows Azure storage is a data service which is geo-replicated in multiple regions, right? And users can access their data anywhere at any time, right? And and this service in 2011, back then it was storing greater than 200 petabytes of raw data. So, so what kind of data could be stored in this? So people can store blobs. So blobs are basically your objects, right? Which can be stored. So your like videos, files, or images, any kind of stream of data, right? Then tables are some structured data. So you can store some structured data in the system. Then queues, we know about queues, right? When we want to store and deliver message, we use queues. So this system can also store that. And then drives, right? So basically when using VMs, you can use network drives. You can mount your VMs through network drives, and these network drives will be storing your data. So this system can also provide that network drive service, which can store your data durably and replicating it, right? Yeah, so these now we'll see like how this one system stores these different kinds of data, and basically it provides high availability as well as strong consistency. So what would be the design of such system? Uh, so this, yeah, so before we go there, yeah, so these are the design goals that and these are the design goals that any large scale distributed data storage system should fulfill, right? That it should be highly available, and it should provide strong consistency. The data should be, so strong consistency is something which a data storage might provide or might not provide. It might provide eventual consistency, but actually this data service provides strong consistency as well. But durability and scalability would be expected from most of the data storage systems, right? So it provides durability by replicating the data across various data center and across geos. And it provides scalability where if if you want to scale more data or store more data, or if the requests traffic is very high, then it can load balance the system to meet your peak traffic demands, right? So both the scalability in terms of storage, storing more data, and compute if you have a lot of requests, how to scale those requests. This system can do that. Cool. So should we move ahead to the design? Are there any questions?
So why do we need here strong consistency? I mean, eventual consistency won't suffice.
So they mentioned that the requirement for the customers, the kind of data they want to store, like it depends on your use case. The kind of data you want to store, you can maybe eventual consistency could be good for you. But this system was designed for those kind of use case scenarios where you need strong consistency. So it will provide you that strong consistency as well. Right. So it depends on your application, what your application needs are.
Yeah, if banking application, then strong consistency.
Yeah.
Thank you.
Okay, great. So basically, like we will see, there are three main components of the system. So the front end system, I mean, load balancer is a common thing which is part of all distributed systems. So these three are the main layers, which is a front end layer, a partition layer, and a stream layer, right? So basically, stream layer is actually storing that underlying data, underlying bytes of data on the storage. But once you have that data stored, you also need some kind of index, right? You need to know that where to look in this entire stream layer. If you're looking for some particular data, where to look for that data, right? So you generally create those indexes, right? And you actually partition the data. And then this somewhere you have to store that what partition stores what data and where the data is located, right? So that partition layer has that purpose, that basically keeping track of where the data is actually stored in the stream layer. Front end layer is like basically the front end, which is request routing, authorizations, and all those things, right? That we expect from the front layer of a system, right? So let's say if a user has to access data, then it will first go to load balancer and then front end, partition layer, and stream layer, and then it will be actually returned, right? And so basically here you will see a concept of storage stamp, right? So storage stamp basically consists of around 10 to 20 racks of storage, and basically they can store 2 to 30 petabytes of raw storage. And in that storage stamp, there are multiple accounts for multiple customers where this data is stored. And basically, once a storage stamp becomes full with the data, then new storage stamps are created, right? So this storage stamp is then also replicated, right? We told for durability. So durability could be like you are replicating your data within a data center, within the racks, right? That is one durability which you get, right? Another is like you also need geo-replication durability, so that if a natural disaster or something comes, your entire data center goes down, then you need geo replication as well, right? So this stream layer, it provides the replication within a stamp. So within a stamp, it will make 3 copies of the data. And so basically this will be within a data center, right? But partition layer, basically, it provides geo replication, that is replicating the data across geo. So we will see how it does that, but basically it sends these commit logs to this another partition layer, and then that will replay those commit logs and then actually create a replica of data in another geo. Cool. And then the storage location service, this is responsible for account allocation when a new customer want to onboard. So like this will be the one which will create an account in one of the stamps. And then basically it is also responsible for geo replication. And whenever there is geo failover, then how to actually route the request and all those things. So this is actually responsible for that.
Okay, so I have one question here. So at the partition layer, the interstamp geo replication, it's happening in a hot manner. Like both the stacks that are seen in this diagram are active, or is it like a passive? Only in case of the disaster it gets activated. How does it?
So
how does this?
Yeah, interstamp replication is active. Like by active means that it will immediately replicate, right? So basically your request will be acknowledged when it is replicated in the stream layer in the 3 copies. And if it is not, then it will not be acknowledged. So it will happen synchronously, but this system happens in background asynchronously. So basically at some particular intervals of time, this will be sending the commit logs to this system and it will be replaying. So this will be asynchronous and this system could have some lag.
Oh, okay. And then it will be okay. So in case of disaster, it will be served from the other geo basically.
Another geo, yeah.
But it won't be strongly consistent.
It won't be strongly consistent, yeah, because it happens asynchronous. Because right, if you are doing geo replication synchronously, then your every request will be super slow, right? Because you have to basically, yes. Right? And basically this geo disasters happen very rarely. I don't know if any of the geo disasters have ever happened where an entire data center has been ruined or something. So basically it helps you from not losing all your data, but I believe that some of your very recent data might get affected, but at least it will save most of your data from any natural disaster, right?
Okay.
Cool. So yeah, so now so we discussed these 3 layers, right? So this is the lowermost layer, then a layer above it, and then the layer above it. So now we will go one level deeper. So we will start from the stream layer. So we will see the stream layer architecture, right? So stream layer is where these bytes of data is actually stored, right? And the stream layer has a concept of extent nodes, and these are the nodes in which the data is stored. And then there is a stream manager component, right? So the stream manager is responsible for assigning that in which extent nodes the data should be actually stored, right? And so this is a Paxos ring of stream managers, which so basically to replicate this data, there is a Paxos algorithm running, and then this information is stored. So we will see in more details these components, but this is the high level architecture. And then, so once the stream manager decides that some stream of data needs to be stored in these 3 extent nodes, then basically the data will be stored there. And so this is also responsible for doing the checksum of all the stored data and basically verifying if all the data is still valid, right? Because like when the data is stored for long duration due to some hardware issues or something, your data might get corrupted in your disks and all, right? So it is important to periodically run checksum of your data and see if the data is still valid. And then let's say for some reason, if the node fails or if the checksum is invalid and things like that, then it will choose another extent node, and then it will replicate the data over there, right? So it will always maintain the 3 copies of the data. Then the layer above it is the partition layer. So similarly, partition layer has a partition master and then partition server. So partition master assigns that which partition server will be storing what partition data. So we discussed this partition data is that where actually the data is stored in these extent nodes, right? So partition server stores this data and partition master assigns that which partition should be storing what data, right? And then there is basically a lock service. Someone had any question?
Yeah, what is the relation between partition server and extent nodes?
So extent node is actually storing your bytes of data, right? And partition server knows that basically which extent node to talk to when you have to access the data. We will see it, like you'll understand it more when we go in like one entire flow of read write request, actually how read and write request goes. But basically this like there might be some confusion here. I told that this stream manager is also responsible for storing which extent node stores the data, but basically stream manager only initializes that what blocks of data in extent will be stored in these for some data that you want to store. So once it decides, then it will give that information to the partition server, and then partition server can directly talk to these extent nodes to store the data. So it will only talk once to this manager, to which will actually tell him that where it can store the data or where it can access the data. Once it has that knowledge, then it can directly talk to them, right? So yeah, so then I talked about partition master. So the lock service, so the partition master also has replicas. So lock service is used to choose a master between these in case of failures. And also another use of lock services that every partition server has to acquire a lease from the locks service and keep on renewing the lease to let know that this partition server is active. And if it is not able to renew the lease, then the partition master considers that partition server as dead, and then it assigns that partition server data to some other partition server, which will be then serving that piece of information of partition.
And what happens if partition master is died?
Yeah, so partition master data is replicated in like it also is kind of a Paxos ring where it is replicated in multiple one of them. And if any one of them dies, so if it's a follower, then a new follower will be set up. If it's a master that dies, if it's a leader that dies, then basically locks service will be used to choose a new leader among them. And then that's how the system works, right? So similar to the consensus algorithms and the locks services that we have seen like Zookeeper and all, it's very similar design over here.
Okay, thank you. And by the way, it looks like we have a point of contention, yeah? I mean, we always have just one partition master, and it can limit our throughput, yeah?
Yeah, but yeah, it can limit the throughput, but we will see in the next step when we will see the request flow, we will see that every request does not go through partition master, and this information is cached, and basically like the request will go to partition servers. So yeah, I'll show you in the next step that why that is not actually a problem. Okay.
So Abhishek, can you explain this Paxos ring? I just missed it. Like, so it's what, like 3 machines are interconnected to each other, right? Is it?
Okay, so Paxos is a consensus algorithm. So basically, between, like, if you want to reach a agreement, like if you want to have an agreement of what the value of something is, right? Then one way is that you store it on a single machine only, right? But then that single machine will always, like, you will get the same request and same response, right? And then there is no problem of consensus. But
So
then there is a problem that if your machine dies, then you lose your data. So you have to replicate the data. But if you are replicating the data, then there might be some lags in the replication and everything. So your entire system should agree on one value, right? So that's what consensus is. Basically, it helps you replicate your data and then also have an agreement, one unified agreement of what the value of some particular data is.
So basically, it is used to avoid the split brain problem, right? What you have in master slave architecture. I mean,
yeah.
if your connection breaks, then even the follower thinks that he's the master, right? So you need to agree to
split brain is one of the problems that can happen, but there are some other problems also that can happen. And yeah, so.
Which are the other problems you mentioned apart from split brain?
So basically, split brain is the problem that you are saying that if there is a network partition, right? And if there is a network partition, then two masters. But what if your master dies? Then what about that? So there was no network partition. There was only one master, and now your master dies. So then how do you reach consensus, right? Because you were always talking to the master and you were replicating it to followers. So then, like, those kind of problems, right? So there are multiple problems. Split brain is just one of the problems. And yeah.
Somewhat belongs to the same family.
Is this Paxos algorithm like a gossip protocol where the nodes will communicate with each other and decide that the node is down?
And like, if you guys are interested in to understand Paxos and consensus algorithms, I would highly recommend to start from Raft, because Raft is also a consensus algorithm. Paxos is very, very hard to understand, but you can easily understand Raft, and then maybe then you can understand Paxos. So if you guys are interested, I can host a session on Raft as well to explain like how basically consensus works and what are the problems that can occur and how these consensus algorithms help to deal with all those problems. Okay.
Yeah, it would be good. Like, we can take one session. I mean,
yeah. And actually, there has been a session on Raft before. So maybe I can share the link for that after this thing. And then if you guys want, we can have one more of it. Okay, so moving on, there are a lot of things. So yeah, so then we discussed about log service, then we discussed about partition layer, then we discussed there is this front end layer, right? So front end is the stateless servers, and basically they are responsible for authentication and authorization and request routing, right? So now I think in the next step, we will see, end-to-end flow. So let's say an incoming write request comes, right? Here you can see an incoming write request come. So the end-to-end flow will be that it will go to partition server, and then partition server knows that where this data is there, and it knows all three nodes where the data is stored. So it will get the data from there, and then, oh, sorry, it was a write request. So it knows where to write the data. So it will write the data to all the three extent nodes. And then when all of three of them have written the data, then the user incoming write request will be acknowledged, right? This is the typical write flow. So let's discuss more about this partition layer, and we will see that why this request actually directly went to partition server, why not to master, and all those details. So now, like, even further, we will discuss the partition layer. So partition layer is basically, we have like these billions of objects that we are storing in this system, and basically this partition layer is helping us basically query, enumerate, and do all those operations on those objects, right? To get that data, right? And the other thing is that basically it is also responsible for load balancing and stuff, because traffic patterns can be highly dynamic. There can be loads in some particular areas, so it has to be scalable, right? And dynamically load balance on what servers are serving which request, right? So so partition layer basically stores this internal object index, right? I told you basically it's kind of an index. Basically, when you have some data stored, and then index helps to let you know that where that data actually is, right? For fast retrieval. So it is kind of that index that you have, index table for each of these data abstractions, right? And this system basically monitors the load also, and it basically will split. So as we discussed, these partition servers are serving the request. So it will monitor, and it will see that if one partition server has high amount of load, then it needs to be rebalanced. So then it will be split into multiple partitions. Or let's say if there are scenarios of merging, when there would be some needs of merge, then it will also do that, right? So now let's see the actual end-to-end how this partition layer works, right? So basically, if you guys would have used Azure Blob Storage, the design overall is something like this: that you have an account in an account, right? In my Abhishek is the account, let's say. So I have a container. Let's say I have a container for Facebook images, right? Let's say I'm creating a container Facebook images. And then in that container, I will be actually storing all the images related to Facebook, right? So this is how I would be storing the data: account, container, and blobs, which is actual data. So let's say in the system, there are multiple accounts, multiple containers, and multiple blobs, right? So this system, basically, it will partition the data based on range partitioning. So there are two types of partitioning of data, right? One is range partitioning. Another is hash partitioning, right? Range is where your data is sorted, and then in that sorted way, you divide the data. That basically data starting from this range to this range will belong to one partition, then this range to this range to one partition. So they have chosen range partitioning, right? So they have divided into these three ranges, and then each of the partition server will be storing these ranges, right? So it will be serving any request starting from A to H will be served by this partition, H dash to R will be served by this partition, R dash to Z will be served by this partition, right? And now who will know actually that which partition is storing which range? Partition master. So partition master has this entire map that A to H is in PS1, H dash to R is in PS2, R dash to Z is in PS3, right? And the front end will actually cache this information so that front end does not have to always directly talk to this partition master, right? Partition map. And then it can, based on the cache, it can directly talk to the partition servers, right? So this is the way to answering the previous question. We have avoided always hitting the partition master by caching this information in the front end server. And only when there is some rebalancing happening, then this map changes, and then we need to update the cache. But otherwise, this will be served through the cache, right?
Yeah, can I ask a question? If we have more than 100 billion blobs, yeah, we can meet situation when all this information will not be able to fit in one partition master map, which should be located in memory. Yeah, I mean we can have huge map, and one host will not be able to keep it. How can we deal with it?
Yeah. Yeah, that's a very good question. So there are two ways to explain this, right? So one thing is that if you know about simple binary tree, binary search tree, or B plus tree, right? So basically you have a root node, like only that one node, right? Where like you have that top level information that which childs to look at if you're looking for that data. Then there are subchilds which have more information where that split is, and then again subchilds of it, right? So the data at the root node is very minimum, right? So if you look at the partition map, it is not actually storing that blob information, that where those blobs are. It is only storing this much information, that if an account starts from A, then you have to go to partition server 1, right? And then all the blobs and every information will be stored in actually this information. So the partition map will never have information more than number of partition servers, right? Because it is basically storing that all the partition servers in a storage stamp, how many, like which partition server is storing which range of data, right? So it will never have data more than the number of partition servers in a stamp.
Okay. Do you mean that it does not keep information about particular blob? Yeah. It
No.
keep information just for ranges.
Yeah, for the ranges, and then these ranges then will have information about the blobs. So basically, like how I was explaining, like if you look at B tree, so this is the root node, and then from the root node, like you know that this A to H are in this, H to R are in this, R to Z is in this. Then so if your information is A to H, then from root node you go to this child. Then in this child, then actually those blob pointers are stored. So in this A to H, now if you have information for A, then this will have pointer over there in the stream layer. So there you will actually have the information that where it is, right? So like from top level, you are going to lower level and dividing the information.
Okay. And what is a storage stamp? What is can we have multiple storage stamp or just one storage stamp?
So storage stamp, basically what they have explained is that it consists of 10 to 20 racks of data, and it is basically like how much information is stored. So I think they store around 20 to 30 petabytes of data in one storage stamp. And so like all the accounts that can fit in one storage stamp, they will be stored in that storage stamp. Once that storage stamp becomes full, then they will create a new storage stamp in that data center or in a different data center, and then it will store more accounts over there.
Does it mean that each storage stamp has separate partition master?
Yeah, so yeah, exactly. So this overall 3 layers we are discussing in respect to one storage stamp. Now, if you have another storage stamp, that storage stamp will also have its own partition map, its partition servers, and basically, right? So
I think one way to understand this is partition map. A partition map master will always be unique, right? And then across storage stamps, there'll be more partition masters.
yeah, each storage stamp will have its own partition master.
Yeah, so it's a one-to-one mapping there.
Yeah.
And then maybe one customer may fall, onto a unique storage stamp, which will have a partition master.
Yeah. So yeah,
so one partition master will never have a full range of partitions. It'll be very partial. It'll be very partial.
It could have like that one account, like one user has so much of data that it has consumed all the storage stamp information, but like as per this design, they don't support storing that much amount of data for a user which spans across multiple storage stamps. So like when I discuss, so if you have that much data that it cannot fit even in one storage stamp also, then you have to create a different account in another storage stamp.
Okay. So one account will always fall into one storage stamp. That's
one storage. Yeah. Storage stamp. Yeah. So basically, storage stamp can have one or more accounts. So it could be one if it is a lot of data, or more, like if it is less data.
Okay.
Right. Okay. Cool. So yeah. So then basically, if the request comes, then it can directly go to this partition server and serve the request from data, right? From there. Okay. So now the point is, like, this information, this tables and all of this partition server, right? This information, how is this underlying? How is this information stored? This table, what we've created, because when you're building your storage system by yourself, like, forget about everything that you have SQL as a table. Like you will think about, maybe you can use SQL or something to store the table, but here, like, you are building your entire storage system by yourself, right? So now the question comes, okay, this is the table information I have, and how do I store this table information, right? So this table information of this range partition, it is stored in the form of LSM trees, log structured merge trees. If you were part of designing data intensive applications, then this was one of the chapters, right? That how basically databases store the data. So there are various ways: append only logs, then LSM trees, then B plus trees, right? So this system is storing the data in form of log structured merge tree. So basically what happens is that if a write comes, first it is stored in memory, right? And then it is also committed to a persistent data storage in commit log stream. And when it is stored there, then it is acknowledged, right? So this log stream has information about all the commits, right? And then this commit log stream is frequently checkpointed and stored in this checkpoint file table, right? And then this data is cached, and basically on this data, index is maintained. So there is this index cache, there is Bloom filters, and then there is load metrics. And so if a read request comes, it will first see in the index if it knows, if in the index cache, if it knows where that row is. If that does not exist in the cache, then it will go to this checkpoint file table from the latest to the last to find actually that row of information of where that data is, right? So by data here, we are talking about this data, right? That this information. Where is my mouse? Oops. Yeah, sorry, my system was so slow. It was processing it now. Yeah, so this file table information, right? So this, we are talking about this row of data, that how are we actually storing this row of data? So, right, and so it is stored in, so yeah, so this row of information, when you want to retrieve it, it is first retrieved from cache or from this row data stream if it is not actually part of the cache, right? And then there is this another structure, blob data stream, which is actually the blob of data, your blob data that you're storing. So this is the overall design of the stream layer. So stream layer basically stores 4 types of data. One is your commit log stream, another is your metadata log stream, right? So these two are log stream kind of data, and this is your data streams, which actually has data. So in data stream, you have this row data, right? Basically any kind of row data about for the rows of the table, and another is blob data. So why they have separated row data and blob data is, blob data basically is that binary data that does not needs to be indexed by itself, right? But these are the rows in the table which needs to be indexed. So this index cache is for the rows of data over here and not blob data stream, right? So let's go now into the deeper of stream there. Let me quickly look at the time. Okay, so we have 15 minutes. So I'll move a little faster and then, yeah. So stream layer. So stream layer is append only distributed file system, and it basically is responsible for storing these files, right? So like the basic design is that first the minimum storage unit is block. So any reads or write that you perform, the most smallest data retrieved or written is in the form of blocks, which is basically 4 MB of data. These blocks are combined to form an extent. And so an extent stores like 1 GB of data. So when it is full, then it is sealed, right? And then basically it completes an extent. So similarly, more data is stored in another extent, and then it is sealed. And then stream is the basically hierarchical namespace where it has pointers to actually like how data is actually organized in sequence. So if you have large amount of data, like if you have 50 GB of data, it will be stored in blocks, extents, and then they will be joined in stream so that you can sequentially first access here. When then this extent completes, then there is a pointer of where the next bytes of data is. So then you can go here and access your data, right? Yeah, similarly extent 3 and extent 4, right? So how is this extent created, right? So basically, when we discussed before, when partition layer wants to write the data, we saw that it directly talks to extent nodes, right? So now let's see how it directly talks to extent node. So first time when it has to store the data partition layer, it will ask the stream master, which is a Paxos layer, that I want to create a extent. So basically I want to store some data, and right now I don't know where to store the data. So please provide me that extent data abstraction where I can store the data. So then it will pick 3 extents from this system, and it will say that, hey, like these 3 are the extents, en1 is primary, en2, en3 is secondary. So now you can start storing your data here. So now once partition layer gets this information, now it can directly start writing the blocks of data to these extents. So now it knows its information. So when it gets the request to write the data, it will append it to like first en1, which is primary, then en2, then en3. They all 3 will acknowledge, and your data will be written successfully, right? So again, similarly, this is kind of a single unit. So it is not overloaded, because only when you have to create an extent initially, then you have to talk to it. Once you create the extent, then you can directly talk to extent nodes, right? So yeah, so some details about these. Basically, we want to store bitwise replica of data, bitwise identical data in extent, and then we want to store the pointers that in this extent, where the block is stored in which extent, and what is the offset to get at that particular block of data, right? So all that information is stored in the partition layer, right? And then replication flow is basically kind of a leader follower. Basically, leader is responsible for deciding the sequence of data, that what will be the sequence, and then the request will go to the leader in that extent node group, and then it will pass the request to the others, right? That we have seen in the previous diagram. So now we have some interesting scenarios. What happens during the failures, right? So let's look at some of the failures. So one of the failures is, let's say we have these 3 extents sealed. Now this 4th extent, it could have stored more data, but now this is not responding, right? So basically what the system will do is it will immediately seal this extent, and then it will ask this stream master to give a new extent, and it will give the new extent, and then they will store the data in the new extent, right? So if an extent is unresponsive, the system gets a new extent for you by talking to the stream master, right? And now, so the data is being stored in the, so this is This is to have high availability. That means that if any of your node is down, like your system is not down, you immediately get a new extent, and then you can start storing your data in the new extent, right? So, and now let's see the logic of how extent sealing works actually, basically. So let's say partition layer was storing the data in extent 1, extent 2, and extent 3, and it has added this red bit of information in extent node 1 and 2, but the 3 has failed, right? So then it will say that I was not able to replicate this data to all 3 of them. So please seal this extent and then give me a new extent, right? So it will, so then the stream master will say, okay, I will seal the extent. So it will ask all 3 of them, right? That what is your current commit length? So they will return 120, 120, and this node was down, right? This node is unresponsive. So, so basically from majority, the stream master has heard that the commit length is 120. So it will seal this information at 120, right? Now, when this extent node 3 comes back up online again, then as soon as it comes back online again, first it has to sync itself with the stream master. So stream master will tell him that, hey, the commit length was 120, you are behind. So like, let me give you the data. So it will give it the remaining data. And so now all 3 of them are healthy, right? Let's look at another scenario of failure and then how this sealing works, right? So basically the data was appended in only one of the nodes, and then the second node failed, right? So then, as we have discussed, partition layer will say, hey, I'm not able to actually append my request. So please seal the extent and give me a new extent. So then it will seal the extent. It will ask for the current length as our logic was. This one will return 120. This one was unresponsive. This one will return 100, right? So now it will take the minimum of these two. So it will take 100 and then it will seal at 100, right? And like, as you guys can see, this is not a problem because this data was anyways not acknowledged to, still not acknowledged to customer, right? So that's why when this is sealed, it will say that you can remove this data because this is not acknowledged. So all the systems have this 100 size commit length, right? And when then this one will come back again, it will tell that the commit length is 100. So you have to remove this extra bit of information. And this was not yet basically acknowledged. So it's okay to remove it. I know like we are moving little fast. So yeah, let's go ahead. If are there any questions so far? Okay. So the next topic is, so the previous topic we have discussed is availability, right? That if an extent node is not available, how the system actually manages to still be available by sealing the extent node group, which was unavailable, and then getting a new extent node group, right? Now let's see that how the system provides consistency, right? So one of the issues in consistency is partition tolerance, right? So let's say there is a network partition, and in the network partition, the stream master is not able to talk to this EN3, but partition server can talk to them, right? So what this system will do is that it basically will see that these 3 nodes have all same information up till this commit length, right? So whatever data is committed so far, it is okay to read from that amount of data, right? So partition server can still read from EN3 and the data which is stored up till here is valid, right? And this piece of data will not be accessible because basically what would have happened was that when the request came to these extent, it was written to first, it was written to second, then it was not returned to third, so it was not acknowledged. So the partition server, since this information was not acknowledged, so in the partition server's index, it does not have information about this thing, right? Because this was never acknowledged, so partition server will never store the index of this data, because according to partition server, this data does not exist. So it only knows about this data, so it can read the data from this node or this node, any of the nodes, right? Even in case of network partition. So this is how they're providing consistency for data streams. Remember, we talked about two kinds of streams, log streams and data streams. So this was the data streams. For log streams, if a partition server wants to access the data. So again, to reiterate, data streams were actually storing the actual blob information or the checkpoint of the information, whereas log streams were storing the commits, right? The commits that we were getting from data. So if we want to access these commits, right, then, and in that scenario, let's say if there is a network partition, so what partition server does is that first it always talks to stream master and asks what is the commit length, and basically, so the stream master will talk to all three nodes, and it will return the commit length from all three of them. So the commit length will be the commit length of sealed extent, right? And so it will say that these two are sealed and this one is not sealed. So only use EN1 and EN2 for loading the information. So then the partition server will only read from EN1 and EN2, right? So in case of log streams, the partition server can read data only from unsealed replicas if all the replicas have same commit length, or it has to read from a sealed replica. Yeah, okay, so I think this this part we moved a little fast. Yeah, probably we would need to spend more time on it. But yeah, so this is this overall how they're providing consistency for data streams and log streams. So now they're almost going to the end. So the discussion is that how basically they are providing both strong consistency and availability. So basically what their point is that we are providing strong consistency and availability only for those scenarios, only for those kind of failures which happen a lot in a typical network, right? And the failures that typically happen in a data center are either the node failures or rack failures, right? So for those kind of scenarios, the system will provide you strong consistency and availability. If there are some other kind of very rare failure scenarios like geo failures and all those things, then the system will not provide you strong consistency, right? So, and basically we have discussed in the previous slides that how this strong consistency and availability was maintained by the system. Availability was maintained by always in the stream layer by creating new extend node as soon as extend node is unresponsive. And for consistencies, like basically the replicas that are created are bitwise identical up to that commit length, right? And so, yeah, so this point is mentioned here that this is designed for specific class of partitioning failures seen in practice, which is either a disk or node or rack failures, right? And not those kind of that entire data center failures where you have to go to a different geo or different data centers. So like some of the design choices and their trade-offs are discussed in the end. So the design choices that they made was first, basically the same architecture is storing multiple kinds of data, blob, table, queues, and writes, right? So this gave them advantage that they can use single stack, single hardware to store different kinds of data. But then the trade-off that they had to face was that it could not be optimized for specific workload pattern because the underlying system is same. So it could not be optimized for like blob scenarios or table scenarios, right? And so this was back in 2011. So now coming to 2021. So now actually that's why they have separated some of the components. So that's why this Azure storage, it is mainly used for blobs now. For queuing, there is different service. For table, there is different service now. Then in the stream layer, you saw that it was always append-only system, that the data was always appended, right? And the advantages of that was that appending, basically replication is much easier, right? And also keeping the snapshot of data comes for free, right? Because since you're always appending your data, so you never overwrite your data. So you always have the history of data. So if you want to look at the history or snapshot of data, that how your data looked at some particular time, you can do that for free when you're storing append-only system, right? And yeah, so again, it also has advantages of diagnosis and repair, right? Anytime you're storing append-only system, like you don't have information, you don't have to worry about your data being overwritten and not being able to replay or diagnose or repair your system. You can always read the append-only system and replay things and do whatever you want to do. Then it also gave them advantage of erasure coding. So I'll briefly talk about erasure coding. Erasure coding is a system where if you want to store 3 replicas of data, you don't have to actually create 3 copies. You can just create 1.5 copy of the data. And that's, yeah, I think we are out of time for this. So I think you can go ahead and look at the slides. These are, I think, should be simple enough.
What is GC overhead?
So GC is garbage collector overhead. So like, because this is append only system. Yeah, I'm just answering this question and then I'll leave. I have
you are
already
able to hear me? Okay, sorry, I was not clear, like you are able to hear me or not. Okay.
Yeah, I'm yeah. Yeah, so garbage collection is useful because like some of the streams which are no longer useful, they have no data is pointing to them. Like we saw in this scenario, right? It created these streams of data, but actually partition server was not storing these streams of data. So then they have to be garbage collected after some time because they are actually not serving any data. So that is what they have to do over here. So yeah, if you guys have more questions, this is the white paper that you can read. I have the link. I will send the link again, and this is the slides. And if you have any questions, you can ask from me. Okay, thank you, everyone.
Thank you, Abhishek.
Okay,
Yeah, thank you, Abhishek.
for the really
Thank
Hey, thanks, Abhishek. Yeah.